Right. Now we will talk about the alternative routes of iron making. So, in this lecture I would be talking some of the processes by which we make the iron either in the solid form or in liquid form. So, these alternate routes of iron making it came into existence mostly because due to unavailability of high quality raw materials such as high grade iron ore and high ranking coke. So, at many places due to depletion of high grade iron ore and generation of more fines, it was difficult to operate blast furnace, or some alternative route of iron making was thought to create. So, this low grade iron ore and the fines can be used, and in fact another driving force has been is the absence of high ranking coke in many of the countries. In some countries there is a depletion in the high ranking coal actually. So, by which you can make the coke. So, these two were quite driving force, and lately environmental problem associated with the blast furnace and with many other industries beside iron and steel industries, power industries and other has forced iron making companies to look for some alternative by which environment problem associated to it can be reduced. So, green house emission of the gases can be reduced, and third is a high capital cost related to the blast furnace operation. This is also an important factor when there is a small city or like that, and you need the supply of the iron, liquid iron, and to make the steel, then one cannot afford to have a big blast furnace at a very high investment. So, that led to development again to an other alternative routes of iron making. So, this led to the development of direct reduction, smelting reduction, mini blast furnace and other new emerging and future technologies. So, in this one we will be talking more about these technologies what have been come into existence until now. So, the first one which is quite old is direct reduction. So, what in short form we call DR processes. So, a process in which metallic iron is produced by the reduction of iron ore below its melting points. So, remember this is below its melting point. So, the product would be solid. Usually the reductants are natural gas or coal based materials. The product is known as direct reduced iron or sponge iron. So, DRI in short what you call it, it is a direct reduced iron which is mostly in the solid semi fused form. So, because it is done below the melting point of it. Essentially it is a process which occurs in the stack region of a blast furnace, which has been discussed in details in this course. So, you are already aware about the iron making in the blast furnace, and in very detail we have discussed about the reaction which are occurring in the blast furnace in various zones, but especially in the stack region where the reduction of iron oxide in various form from hematite to magnetite to bushite occurs. those reactions are applicable even to the direct reduction, because even in the upper part of the blast furnace in the stake region, iron whatever is reduced is still in the solid form and not in the liquid form, and same thing happens even in direct reduction. So, there is a big familiarity not in terms of just physical, even the chemical reaction or physicochemical way, whatever processes are occurring in the upper part of the blast furnace, same thing can be applied to the direct reduction processes. So, most of the processes therefore have the reduction shaft similar to the blast furnace stake, either in packed bed or fluidized form. So, that is actually one difference. So, it can be either in a packed or fluidized form where it is reduced into solid iron. So, the main advantage of DRI is elimination of coke and thus reducing some environmental related problem. So, you must be aware that coke making is a very nasty or dirty process which involves volatilization of coal, the coke oven, and that creates lots of environmental problems. So, this is the biggest advantage of DRI, that you do not need coke as a reductant, but you can use the coal for that purpose, and in that way you also reduce some environmental related problem, and it is much more advantageous when especially in those countries where high ranking coal is not there. So, one can use the coal and can make the DRI. So, it requires less capital and a smaller unit, and the process control is easy because unit is small, there are not much complications. So, process control becomes quite easy. However, it suffers from lower productivity, naturally it is a small unit and few other problems. So, productivity is low, and final product has to be melted for further use, which has less carbon content. And if you remember, we talked already about melting point and other impurities which can affect the melting point of iron. So, if the less carbon is there, melting point usually becomes quite high. So, carbon reduces the melting point of iron quite substantially. So, here in DRI, direct reduced iron, you have a less carbon. So, you need then more energy to melt it later. High porosity in the final product, and this leads to the reoxidation. So, due to the, because it is the form of in sponge, more porosity is there, it gets reduced. So, due to that lots of porosity is there in the reduced solid iron, and when it comes out, so that time one has to be very careful, it should not be exposed to the air, otherwise it may reoxidize. And it is not only that, even a storage problem in during transportation, it may lead to the reoxidation. So, these are some associated problems with the DRI, but it can be easily handled. So, before describing the kinetics and reduction mechanism of direct reduction, there are two terms which one should be familiar of, and usually DRI is quantified in terms of percentage reduction of iron and percentage of metallization, sometimes you call it degree of metallization. So, these are defined below. So, when you say percent reduction, it is actually nothing, it is a ratio of weight of oxygen removed from the ore and weight of oxygen present in it into 100. So, that gives you the percentage reduction. So, whatever oxygen is removed from the ore and the total oxygen which is present in it, divide by that and multiply by 100 will give you percent reduction. And so, the above the definition also has come due to the gradual removal of oxygen atoms from the iron oxide as shown below. So, as he said, it is a removal of oxygen from the ore and the total oxygen present. So, if you look at the way ore our iron oxide is present in any of the iron ore, first one is hematite, which you are already aware. So, when it goes to hematite to magnetite, it actually removes about 48 atoms of the 48 sort of oxygen is removed, whether you can say in moles or kg moles or gram mole. So, that much oxygen is removed from hematite to magnetite, and when from magnetite to wüstite it is reduced, 80 mole sort of oxygen is removed in terms of tons or kgs when you do it, and from our per ton basis we take it 48 kg, 80 kg, and from wüstite to iron about 302 kg of oxygen one has to remove, then you get iron. So, you can see from wüstite to iron the maximum oxygen is removed. So, oxygen removed from each oxide is shown above the arrow in each step and has been discussed before in previous lectures. So, if you go the physical chemical behavior of the iron oxide in the blast furnace, where we discuss in detail about the reaction kinetics, reduction of iron oxide in various way, and even the optimization, in that one all these things have been described. So, I would encourage you to go to those lectures, and in brief I will also take it again here. So, based on percentage reduction, it can be estimated that the percent reduction in each step would be 11.1. So, from Fe2O3 to Fe3O4 it would be 11.1, from Fe3O4 to FeO is 29.7, and from FeO to Fe 100% percent reduction. So, it is clear from the percentage reduction that up to almost 30%, if you look at up to here, up to almost 30% reduction of iron ore, no metallic iron is formed, only wüstite will form. So, it starts forming only after 30% reduction. So, therefore, one has to define a degree of metallization of our percentage of metallization in a different way, because only after 30% of reduction the metallic ion come into the picture. So, the extent of metallic ion formed is given by percentage of metallic ion equal to weight of metallic ion divided by total ion weight in the sample into 100, that will give you the percentage. So, weight of metallic ion which is formed divided by the total ion weight in the sample, that will give you the metallization or degree of metallization. So, percent metallization and percent reduction are correlated as. So, it is a empirical correlation which has been found between the degree of metallization and degree of reduction. So, percent on metallization equal to 1.43 into percent reduction minus 42.3. So, from this equation you can see this is a linear equation. There is a linear relation between the percent metallization and the percent reduction. So, when you draw a line, it will give you a straight line cutting on the x axis. So, and if you know the percent reduction, you can probably from this relation calculate the degree of metallization. So, once now you are familiar for this, because this term usually degree of metallization and percentage reduction is quite useful in describing the efficiency of the DRI process, and more than 90% degree of metallization is needed in direct reduction process. So, 94, 93, 95% or so, or sometime even up to 96-7%. Now, it is about the kinetics and reduction mechanism, which is again an essential part for any of the process or new process when you have. So, kinetics of the process is similar to the blast furnace stack region, which has been discussed in details in the previous lectures. However, just to summarize, the most common reactions are written below. So, based on both CO-CO2 ratio, this is CO-CO2 means mostly the coal based reaction, and H2H2O ratio, this is actually you get mostly from the natural gas based reaction. So, DRI, direct reduction, can occur by two of the process which we will discuss in detail later. So, these two processes are either coal based, so carbon as a reductant, or natural gas. So, hydrogen is a reductant in combination with the carbon also, CO plus H2. So, we have already discussed about this system and carbon oxygen system. If you go back to our previous lecture, and similarly about this we have discussed a bit in relation even to the discussing about injection of moisture H2O or oxygen through the tube in order to increase the reduction efficiency of the gas, and that time we discussed about this system also. So, I would encourage you to go through that, but in brief I am taking it again here, but I will not go much into the detail because this has already been discussed before. So, three thermodynamically stable species of iron oxide, as you are aware, hematite, magnetite and wüstite. This is stoichiometry, this oxygen association or the percentage associated with iron changes. So, it is not a stable oxide, which we said before also. So, hematite due to magnetite due to wüstite and gives the iron, and this is a partial oxidation of the carbon which gives you the CO, and heat is required for that. But for complete combustion you get the CO2 and heat is released, in that way you produce more heat. And if you look at the previous lecture and go through this, we have already discussed about this reaction, how hematite converted into magnetite by CO at 900 degrees centigrade. So, we are here talking about the DRI, which is usually the temperature is about 9, in fact temperature ranges from 700 to 1000 or sometime only to 1100 it may go. So, it is mostly in that range, but usually this is sort of a temperature which is maintained in most of the reduction shaft in DRI or even in the fluidized bed, about 750 or like that sort of temperature, 700. So, these all reactions and their kinetics is applicable even for DRI. So, hematite to magnetite at 900 delta G was given. So, if you look at the equilibrium constant, it's very high, and that gives the percent of CO utilization almost 0. So, it's very easily reduced, which we discussed before, and from magnetite to wüstite, it's your K2 is low, and it's about 0.25 this ratio comes. So, this still needs less CO, but can be reduced more comfortably, but of course harder than the magnetite. And when we go to the FeO to Fe, and then your equilibrium constant value is very low. So, you need a high reduction potential or high reducing power of the gases. So, that is where you have CO2 ratio of 2.3, and it is clearly also we talked about the efficiency of the reaction and utilization of the CO factor when we put it this ratio for respective of these three reactions. We will find hematite to magnetite is almost 100% CO utilization, and for others, for magnetite to wüstite it's about 80% utilization, that factor. So, it decreases. However, because here you really need a very high reduction potential, and the utilization factor for from wüstite to iron is just about 30%. So, again, which means you have to introduce a very high reduction potential gases from the bottom. So, FeO can reduce into iron, and it then loses this reduction potential power. So, and which you do not need that much in the upper at it goes up in the upper part of this shaft, whether it is a blast furnace or direct reduction. So, it can easily reduce magnetite to wüstite, and then you need a very little CO percent or the reduction potential to convert hematite into magnetite. So, from the bottom you send a high potential reducing cases. So, it can reduce wüstite to iron. So, this is FeOC carbon system. Of course, because this has been taken from the previous lectures. So, here this is not applicable, because this is a separate part of producing reducing gases in direct reduction processes, while in blast furnace it is in one reactor, it is a part of it. So, we want so this is not relevant to the direct reduction process. However, these reactions are quite relevant to direct reduction processes, that hematite to magnetite, magnetite to wüstite, and wüstite to iron, and below 1000 degree or 9 CO is a bit unstable and goes to CO2. So, overall reaction if want to give in the upper region, then by gauge reduction it can be written in this way, which is sort of indirect reduction, which has been discussed quite in detail previously, and similarly the other way in form of with the carbon with the above, the overall reaction takes in this form, which sometimes you also call the direct reduction if it is lower part of the blast furnace, but this is not relevant to the direct reduction process, and mostly this is the one which is more relevant. And the overall reduction reaction by hydrogen usually. So, this is mostly by carbon, and this is mostly by hydrogen. The way to give overall reaction with the CO, this overall reaction with hydrogen, similarly it is given by this reaction from hematite to iron, the overall reaction. Now, here hydrogen actually you get it through the natural gas. So, these are the gas based reduction whatever we discussed here. These are the coal based or solid sort of based reaction through which you get the CO, and this is a natural gas based DRI reduction. And usually in the natural gas, methane is the major part of it. So, you can't use as such the natural gas. So, it needs reforming. So, before utilization of it. So, major component in natural gas is methane, which is reformed by oxidation. It is a methane, ethane, other hydrocarbons. So, by oxidation in presence of suitable catalyst, usually it is nickel, we will talk a little later, and the right temperatures. So, it gives a mixture of hydrogen and CO. So, by adjusting the temperature, catalyte pressure and other parameters, one can adjust this ratio. So, can have a highly reducible gas from the reformer. So, natural gas first pass through the reformer, and then these gases are used for the reduction purpose. So, in case of hydrogen, just pure hydrogen, the process usually is chemically controlled, but in case of CO, it is both chemical and diffusion control gases diffusion. It could be even combination, depends on many situations. Porous iron oxide, the activation energy is much lower in porous iron oxide, and process is controlled mostly by gaseous diffusion. If iron oxide is very, if it is very porous, then even we will talk about that a little later. Now, many times what happen, carbon deposition occurs, and this actually we had discussed again in the in terms of blast furnace, that Woodward reaction, carbon deposition reaction. So, that also occur at less than 900 degrees Celsius, and sometimes the cementite is also formed, and sometimes it is good in direct reduction, it reduces a little melting point, and not only that, also it is reoxidation of iron is prevented, or at least it is reduced by forming this iron carbide, and this in one way also good when it is used as a feed. So, carbon percentage is increased in that way. So, prevent reoxidation, lower the melting point of TRI when this reaction occurs, and sometimes it is needed to do this.